Start பண்ணுறேன். Good evening, everyone. Vanakkam. Thank you so much for joining us today. Yes, the topic is Introduction to Metal Organic Frameworks, which is somewhere related to the chemistry. And I have with us Vasan, my friend here. Vasan, very good evening, Vasan.
Good evening, SOORIYAOLI.
Yes, thank you so much for joining, Vasan. So it is time that we should start the session. So we can go on starting the session now.
Yes, thank you. So, good evening to all. I welcome you all to my talk titled Metal Organic Frameworks. So, for those of you who do not know me, I am Vasanta Kumar. I am currently pursuing my research at National Institute of Technology, Tiruchirappalli, under Professor R. Karvembu, and my main area of interest is metal organic frameworks for the catalytic conversions. So, my research area is I use metal organic frameworks for some important chemical conversions. So, and I thought I should introduce you all to a metal organic frameworks and to highlight you or to enlighten you with a term called as metal organic frameworks, because I found it to be a promising material for the future. Metal organic frameworks are a 3D polymers. So these are called as 3D coordination polymers. So it is not one-dimensional or two-dimensional. So this is a 3D polymer in which it exists. So these are crystalline porous materials, whereas the other materials which are like polymers or which are 3D, and most of them are not crystalline. If they are crystalline, they are not porous. It is very difficult for us to see a material which has got a crystalline property as well as a porous property. And these metal organic frameworks are basically synthesized by di and tricarboxylic acid with bi and trivalent metal source. So I know it is a little difficult to understand all these terms. And then in the coming slides, I will explain one by point. So these are usually synthesized in solvothermal conditions. And a very important and very interesting property of this metal organic frameworks is isoreticular synthesis. So the term isoreticular means retaining the same structure and enhancing its property. You can see there is an yellow color diagram here, and this diagram conveys what is isoreticular properties. The yellow color is the cavity inside the frameworks, and by keeping the shape, which is like a cube-like structure, we can increase the size of the cavities. So this is called as isoreticular synthesis, and not many materials have such kind of a property. So this is one of a very interesting and important property of a metal organic framework which it possesses. So I said metal organic framework consists of three important aspects in them. One is a node, the other is a spacer, and other is a cavity. So cavity is nothing but an empty space. So these empty space makes it to be a porous material. And nodes are nothing but the metal centers. So metal centers constitute nodes. So each metal center is connected by a linker, or it is called a spacer. So these spacer connects these two metal centers, so which forms a cube-like structure or a cube-like porous material. So these are the crystalline porous materials. So it has got a definite shape and a crystal structure. Whereas the other non-porous materials, those we have this coal or charcoal or carbon-containing graphene, all those porous carbons does have pores, lot of pores, and the surface area is large, whereas it is not crystalline. So this metal organic framework is crystalline. In the same way, it is porous in nature. And the background of this. So metal organic frameworks are born from zeolites. So zeolites are already existing porous crystalline substrates which is present in nature as well as in man-made. So the general form of zeolites are aluminosilicates. So zeolites are composites where aluminium and silicates form together to form a porous three-dimensional polymers which are used mainly in chemical industries as catalysts and as absorbents. We would have come across zeolites in many forms, but no one knows this is a zeolite. The metal organic frameworks for the next generation zeolites. So it has got a very very high surface area as compared to that of the zeolites. One of the development which is a joint venture from Sigma Aldrich and BASF. Both are top rated chemical companies. So they have synthesized a metal organic framework which has got a surface area which is equivalent to that of a football field in 1 gram of a substance. So if I take 1 gram of a substance, the active surface which is available for a molecule to work on is around 40,000 square feet. So 1 gram of material has such a huge surface area, which is like a benchmark in the surface materials. So the term metal in the metal organic frameworks refer to nothing but a metal. So I thought I should introduce metal. What is a metal? So metal. So this is the periodic table of elements which are known to mankind. So and most of the blue color highlighted are metals, and those which are yellow color highlighted are non-metals. And metal constitutes most of the component of the known metals, known material to us. So and one important metal which we all know, which are familiar, are gold as well as silver. So this gold and silver are used in a native state, which is like not metal oxide or in any other complex. It is used as such. Similarly, there are copper, lead, tin, as well as zinc and nickel are also used in its native state. So metal possesses some unique properties, which is like luxure, which is called as shining. So if the metals has the property to shine, it has a property to be malleable and ductile, which can be beaten into sheets or drawn into wires. So and metals are good conductors of heat as well as electricity. So the other important property, other important property for a metal is sonority. So metals consist of a very typical sound, which we call as sonority or a metallic sound. So metal tends to form a positive ion by giving off electrons. The other one is metals forms ionic as well as covalent bonds. And here are a few examples of metals which we come across daily or which we take into our body daily. One is sodium, the other is potassium, and the other is iron. So these are the very typical forms of metals which we intake in our daily food and which are very, very essential for the life or the normal functioning of a human body. So decrease in the quantity of any such decrease or increase in the quantity of any of these three metals can have a severe effects on us. So sodium we intake in the form of a sodium chloride, which is called as an ionic compound, whereas the iron goes into our body in the form of a heme. So whatever proteins we eat generally contains iron in the form of a heme. So these are the two forms of metals which exist popularly, and the one is like ionic form, the other is like complex, metal complex. So here we have to concentrate on what is metal complex. So metal complex consists of a metal center. In this case, it is an iron, and this heme is the same heme as which is present in our hemoglobin also. So this contains an iron center as well as an organic moiety which is called as a ligand. So a metal complex contains a metal center as well as an organic compound, organic moiety which is called as a ligand. Then metal complexes are more stable than its ionic form as well as metallic form. So if I take a metal and keep it in its original form, then when I convert it into a metal complex, the metal complex tends to be more stable when it is compared to the metallic form and in the ionic forms. Organic is the ligand part. So the ligands are made up of organic molecules. So ligands are the organic compounds which contains heteroatoms in it. So the heteroatoms act as the building blocks or the binding sites to form the metal complexes. So these are otherwise can be termed as an anchoring sites, in which these heteroatoms functions as an anchoring site and then bond to the metal centers. So the most common heteroatoms which are present in the ligands are oxygen, nitrogen, and sulfur. And here are the few examples. The one is hydroxide, cyanide, water, ammonia. Yes, water can also act as a ligand. So it coordinates to a metal center via the oxygen bond. And ammonia, which is very importantly used for the synthesis of urea, can also bond to the metal via nitrogen. And carbon monoxide as well as thioisocyanide. So we say the carbon monoxide is toxic to human because when we inhale carbon monoxide, the carbon monoxide bonds a very, very strong bond with the heme, which I showed it in the previous slide. The carbon monoxide bonds very strong to the heme, so that these nitrogens are removed, which means like the hemoglobin stops functioning, which means the intake of oxygen is reduced. So thus carbon monoxide is toxic to humans. So because of the binding nature, because carbon monoxide binds more strongly than the heme proteins. Ligands can be classified in many different ways, and based on the number of anchoring sites, which is like binding sites, ligand can be classified into monodentate, bidentate, and tridentate ligands. As well as if we have more than 3 sites, it can be called as polydentate ligand. For example, here we have 4 molecules. One is benzoic acid. In benzoic acid, we have got an moiety called as COOH. The oxygen moiety can bond to the metal centers. The oxygen moiety can bond to a metal center. If you have a metal here, it can bond to a metal center. Similarly, we have got a terephthalic acid which has got 2 binding sites. So it is called as a bidentate ligand. We have got a tricarboxylic acid which has got 3 binding sites. So we call it as a tridentate ligand. So it can also be termed as denticity. So which is like monodentate, bidentate, and tridentate ligands. So these are very important terms for the when we want to understand what is metal-organic frameworks and how do we synthesize metal-organic frameworks. So these are monodentate ligands, bidentate ligands, and tridentate ligands. And these are the other examples of bidentate ligands. So in this case, it is ethylene diamine, in which nitrogen can act as an anchoring site for the formation of complexes. Similarly, these are same kind of nitrogen, but it is a different kind of a molecule, which is called as bipyridine. Similarly, oxygens can also act as an bidentate ligand by anchoring to the metal centers, which is called as acetate, and this is called as oxalate. And choice of ligands for the preparation of metal-organic frameworks. For example, if I take a benzoic acid, remember I said like metal-organic frameworks are 3D polymers, so they need to extend in all 3 directions. So if I take a ligand of benzoic acid and then I try to make a complex, so let's assume like this red color is this part and then the blue color is the other organic part. So this is the anchoring, the red color is the anchoring side, whereas the blue color is the tail part. So the metal center binds to an anchoring part, and since the metal can coordinate with 3 other metal centers, let's assume like a metal can coordinate or can attach to 3 other anchoring sites. So now this is saturated, it cannot extend to the other dimensions. Whereas if you have a terephthalic acid which has 2 anchoring sites, so this is one ligand, so we have got an organic part, and at the both ends we have got an anchoring sites. So now this can this one ligand can anchor between 2 sites. So similarly here also, now I have got 3 vacant sites and it can be extended this way. Similarly, I can put in one metal center here, and which can be extended and extended. And this structure can be extended into a 3-dimensional structure. Whereas this structure with this ligand, it cannot be extended into a 3-dimensional structure. So if you have to prepare a metal-organic frameworks, I have to avoid using benzoic acid, whereas terephthalic acid is favored. Similarly, when we have tricarboxylic acid, this is also a tricarboxylic acid, and whereas this is also a tricarboxylic acid. The difference is it is present in its 1, 2, and 3 positions, which is present in 1, 2, and 1, 3, and 5th positions. So if I have it in this form, it can be extended into 3-dimensional structure. For example, this can bond to a 3 different metal centers, and these 3 different metal centers can again bond to a 3 different ligands. So which can be extended 3-dimensionally. Whereas in case of 1, 2, 3, it can be saturated here only. It cannot extend this way or this way. Whereas it can be extended in X, Y as well as Z directions. So if you have to choose, this could be the choice of ligand for the preparation of metal-organic frameworks. Whereas this cannot. With benzoic acid and with tricarboxylic acid, I can prepare only a metal complex, not in 3-dimensional extended structure. So if I have to prepare a 3-dimensional extended structure, I have to choose a ligand which has got an symmetry between them. Like it should have end-to-end symmetry, like in the one end and the other end. In case if you have got any doubt, and you can comment in the comment box, I'll reply to it immediately. please feel free to stop in between so that others can also understand if they are willing to ask. So the general choice of metals for the preparation of metal organic frameworks are aluminium, calcium, chromium, iron, and zinc and zirconium. So these are the cheap metals which are not noble metals. So metal organic frameworks use such kind of a very cheap metals to prepare an important structures. You can see like these are the examples of ligands or linkers which are available, and this is called as benzene dicarboxylic acid. Previously, it was named as benzene benthalic acid. So these and this structure is same, but you have got a different in its one position. We can see there is a small substitutions which are present in all these places. So these make them unique. If you have to prepare a metal organic framework with BDC, it would be simple BDC. Now, if I use a bromine molecule to introduce on it, I am introducing a different electronic property or a different chemical property to it. So by altering the small changes in its positions, we can alter its physical properties as well as chemical properties. Physical properties like the properties in which the material can absorb molecules or adsorb molecules. Chemical properties are like the catalytic properties, or it is toxic or non-toxic as well as. So for example, if I include a functional group called as OH, the molecule can easily absorb water. If I introduce a functional group called as CH3, this ligand, I introduce a hydrophobic property to it, and the hydrophobic property can be increased by introducing this molecule. Whereas hydrophilic property can be which is like water-loving property, can be introduced by involving fluorine molecules or alcohol molecules. So such kind of a property can be altered. This has got a metal organic framework has got such kind of an advantage, whereas the other materials do not have such advantages, in which this small tuning of chemical property is not possible in those other molecules like zeolites. In this case, we have got previously I mentioned something called as isoreticular synthesis, which means like the chain length differs, whereas the whole structure of the molecule remains the same. So these are such compounds which can be used for synthesis of isoreticular metal organic frameworks. There are other ligands which are called as bipyridine structures, which can interact with nitrogens also. So synthesis. Metal organic frameworks are synthesized in two ways. One is solvothermal techniques, the other is magnetothermal techniques. Solvothermal techniques are generally like you take a ligand and you take a metal salts, and these metal salts, let's assume these metal salts are dissolved in a solvent. If it is water, it can be called as hydrothermal synthesis. If it is any other solvent, it is called as solvothermal synthesis. So, for example, now we take water, and this water is metal salt as well as the ligand is dissolved in water, and if we heat that solution to a temperature of above 100 degrees Celsius, this is called as hydrothermal synthesis. If I take a solvent other than water, which is called as DMF or DMAC, something like that, dimethyl formamide, if we take a solution of such kind of a compound, and then it can be called as solvothermal synthesis. Heating of that solution above its boiling point is called as solvothermal synthesis. So if we heat the solution above its boiling point, it is called as solvothermal synthesis. And these solvothermal synthesis produces highly porous materials and highly stable materials. Whereas magnetothermal methods is just grinding of two substances. It can be like two solids or two liquids. So these can be put it in a mortar and dissolve and grinded it to fine powder. So these fine powders can also give us in metal organic frameworks or a 3D porous materials. And the porosity is not as good as that of solvothermal techniques. Solvothermally prepared metal organic frameworks are more stable to a chemical as well as thermal conditions. Whereas magnetochemically prepared metal organic frameworks are less porous and less porous. It is also like not much thermally stable and not much chemically stable. And here is one such example of a metal organic frameworks. and it was prepared with iron or chromium salt. It can be prepared with either an iron salt or a chromium salt, and then substituted benzene dicarboxylic acid. The R stands for the substitution. Previously, we saw like OH substitution, BR substitution, or methyl group substitutions. So these substitutions can be referred as R group. So with this, I can prepare a metal organic framework which has given us name as MAL88B. So this MIL stands for Materials from Institute of Lagos. So these materials like metal organic frameworks, if we discover it, if we find a new metal organic frameworks, these can be named after the institute or after the lab name. So it has gotten such kind of an advantage. So this is the 88 material which is prepared from the Institute of Lagos, which is in France. So the structure of material is like this. So it has gotten porous structures. There are a lot of voids in it, and there are this moiety is the one which you see it in grey color and red color, and those are the metal centers here. So this is one such example. So I wanted to show it to you. So when we see the structure of the molecule, like with the microscopes, and these look like this. It's like a spindle-shaped molecules. So this molecules especially has gotten one important property, like it can vary its size in different solvents. If I take this material, it will be like powder in structure, shape. If it is sprinkled with small amount of water, it can swell up to 700 nanometer. If the water was substituted by methanol, it can swell up to 800 nanometer. If I put it in another solvent called as dimethyl formamide, it can swell up to 900 nanometers. So this is one property of a metal organic frameworks which can be exploited also. So this compound is thermally stable as well as chemically stable. So the applications of metal organic frameworks are in various fields like supercapacitors, lithium-ion batteries, electrocatalysts, photocatalysis, and chemicals for the production of fine chemicals, catalysts for the production of fine chemicals, as well as sensing. So I'm going to give you like few examples of metal organic frameworks and its application. So these can be used for the introduction of drugs into our body, which is called as drug delivery. So these metal organic frameworks can act as a carrier for the targeted drug delivery. In case of chemotherapy, like in cancer cell lines, it has to be very, very targeted chemotherapy. If the drug delivery is very targeted, the cost is the cost of treatment is minimized, and the cost of drugs are also minimized, and then the side effects are also minimized, because the side effects are the one which is very high drawbacks in case of chemotherapy. So these metal organic frameworks can act as a loading material for the drugs, and it can deliver. We can fine tune the chemical properties in such a way that it goes to a particular spot and then it delivers the drugs. And these metal organic frameworks can be designed such a way that it is biodegradable and non-harming to human beings. So, so with the help of isotopic glass synthesis, a large metal organic framework can be synthesized in a small, can also be synthesized with small size. So with holding the chemical and physical properties. For example, I find a metal organic framework which is of large size, and I find it to be efficient drug delivery system. But the pores in the cells are very, very small, which is of very narrow size. So this can also be reduced with the help of an isotopic glass synthesis. So metal organic frameworks, we can with the help of suitable ligands and transition metals, it can reduce the toxicity of the human body. So when we take into our human body, the toxicity can be nullified also. Like if you take an iron compound or an iron metal organic framework, which cannot be toxic to human at all, because when it degrades, it produces an iron as well as a terephthalic acid, which are the components of human body. So which can be absorbed by the human body or given out by the human body, which is not toxic to humans at all. So this lowers the required doses, also extend the time of medication in our body. Like since it is a very targeted mechanism, the exposure or the healing of the cancer cells are very effective, and the side effects are highly reduced because the cells are highly targeted and it is treated. So as I said, like the large MOFs or metal organic frameworks can be condensed into a nanomorphs. So this nanosite reduction allows it to be systematically circulated throughout the body, but retaining the property of the bulk metal organic frameworks. If the metal organic frameworks is large and it has got a good property, even when we synthesize it at a nanometer scale, it still holds the properties of the bulk MOFs, but it is of small size so that it can be circulated in the veins as well as the blood cells. And this metal organic framework called as MIL-101IN was used for the imaging purpose. So this is when a drug is introduced to it, we can find out where the drug is exactly released and what are the other parts or the vital organs in which the drug is present. Suppose if I have a particular type of cancer, and if I administer the drug and then the drug is spread throughout the body, but it cannot affect the whole body. So we can monitor the movement of drugs with the help of the metal organic frameworks. So with the help of this, the images can be occurred, which is like fluorescence imaging or MRI imaging, and then we can find where exactly the drugs are. Which in other words is that if we locate where the metal organic frameworks are, we can locate where the drugs are. The drugs are loaded onto the metal organic framework so that for the future, we know we can follow it up where it is moving on. It can also be used as an molecular rotors. We have seen missions or engines, which happens in the all vehicles, which is present in the all vehicles, and there are molecular missions which are also be present there. And this was made to be possible with the help of MOFs. So these replaces the liquid crystals for the optoelectronic studies. It can be called as a light stimulus. So if we apply some mechanical force, these molecules can bend together. For example, we have seen a self-repairing polymers. So these self-repairing polymers are basically which has got a molecular rotor property in them. So these self-repairing polymers or self-repairing tires which we use in wheels or all have such kind of a chemical properties. So metal organic frameworks can be used for such kind of applications also. So this is like metal MOFs as a catalyst for the fine chemicals. And these are the few chemicals which are highly important. So these two chemicals are called as biomass derivatives. So these two are used as fuel additives currently in the petroleum industries or in all petrols which we use. They have these both compounds to increase the combustion. But the cost of this compound is very high. So use of such metal organic frameworks, which are like iron based, which are quite cheaper in nature, to convert these chemicals into in its active form. So which can also, this is one of an example in which the metal organic frameworks acts as a catalyst, important catalyst for the synthesis of fine chemicals. And there was one more report in which they have used metal organic frameworks for the capture of CO2. We know like carbon dioxide is one of the greenhouse gas, and it is people strive long to reduce it. Nowadays, people have found a way to selectively remove carbon dioxide from the atmosphere. So MOFs has been used as one of an efficient compound to recover only carbon dioxide. So it can selectively absorb just carbon dioxide, and if needed, it can be converted into a methane, which is called as a fuel. So it can be converted into its useful form also. If it is not converted, it can be stored also. So carbon dioxide can be selectively absorbed as well as it can be stored. Similarly, the synthesis of the development of fuel cells are currently in the market. So if we could successfully store hydrogen safely, then the fuel cells are possible. So metal organic frameworks has an important part in it. So recently, in 2018, a group from US have published an article saying that they have reached the highest point in which metal organic frameworks can store hydrogen. They can store 100 liters of liquefied hydrogen in 1 kilogram of MOF. It's like very huge. So if such thing happens, we can store hydrogen very safely and very efficiently, and this can be given off very efficiently so that the fuel cells are possible. So metal organic frameworks have it has an opportunity to engineer to improve its activity. Here is one example which we have seen earlier, which is called as MAL88B, and I said this is made up of either iron or chromium off. And recently people have changed this. Like instead of having one metal centers, they can prepare a molecule which has got two metals, which is like instead of just iron, it has got as bimetallic MOF. So it can also be called as mixed metal MOF. So and this is called as a Poultry-Savvy data, which says like both the structures are same. So single metal as well as mixed metal. So both these MOFs have similar structure, but the properties are very different. The surface area of the single metal MOF, the surface area of single metal MOF is just 40 meters square per gram, whereas the surface area of a mixed metal MOF is like 350 meters square per gram, which is like 78 to 80% increase of its surface area. So, which means like the surface area is more, so the catalytic activity can be more.
People just stay connected. We lost Vasant in the connection. We'll get him back. Just stay connected.
Sorry everyone, like there was some technical issues. I got disconnected and I'm back again. So I was previously saying the mixed metal metal organic frameworks have an enhanced property. Like in this case, it is like surface area. So this surface area enhancement can be seen in its activity, catalytic activity. For example, previously when a single metal metal organic framework was subjected to a conversion of linoleic acid to gamma vanillolactone, it was lactone. We could say like the conversion took around 10 hours, whereas for the conversion using bimetallic framework just took 17 minutes, which is like from 600 minutes it has become like 70 minutes. So increase in the surface area has improved the reaction time. Similarly, the previous reaction with single metal metal organic frameworks, it took around 9 hours, and now it just takes around 40 minutes. So the activity can be improved by introducing appropriate change in the metal organic frameworks. So metal organic framework has got such capacity to be engineered so that the chemical properties can also be enhanced. So metal organic frameworks has got a limitless potential in many fields. Like it has got high surface area. It can be used in biomedical application. It can be used for the electrocatalytic application. And for the solids also, it can be synthesized by solvochemical methods. And these solvochemical methods has to be improved so that the activity or the stability of the molecules was very high. So it has got a very unique electrical properties which have been still to be explored. I think this kind of presentation, if you have any questions, you can ask me. Or if you can type in the comment box, I will reply.
Yes, thank you so much, Vasan. And people, if you have any questions, we are open for questions. You can just type your questions, or
Thank you, Ali.
you can just go on directly asking the questions to Vasan. So we'll be having one more session also, people. That will be an advanced one. So,
Hello, sir. Can you hear me? Sir?
Yes, I can hear you.
Sir, can I know the difference
Yes, I can hear you.
between rigid MOFs and flexible MOFs?
The flexible MOFs have generally got a longer chain length in its molecule, as that I informed you in the isoreticular synthesis. Show you an example. The small molecules or small MOFs can be called as so for example, this can be termed as a rigid MOF, and this can be termed as a flexible MOF, because the longer the chain length, the flexibility of the structure is more. So it is like that.
Oh, okay. Thank you, sir. Thank you, sir.
And in comment box, we have got a question like distinguish between like metal organic frameworks, which is MOFs, coordination polymers, and metalomers. Metal organic, the bigger classification is like coordination polymers. So all these comes under coordination polymers. And if we have a one-dimensional structure, in the previous slide, during the introduction, I said metal organic frameworks are three-dimensional polymers. Which is like if you have one-dimensional or two-dimensional, it is generally called as one-dimensional coordination polymer or two-dimensional coordination polymer. if we have a three-dimensional structure, it can be termed as a metal organic framework. And this structure has to be repeating on its own. It has to be crystalline nature also. Thank you, Satish Anna. Here is a question like the application of the compounds MOFs are chosen on their basis of metals or ligands. So I think it is the combination of both. So it depends on the activity in which you are going to study. Like it has to be a balanced properties of both metal as well as silicon. If I have to prepare a cheaper catalyst, I have to go for a cheap metals. If I have to go for an very advanced or high active metals, it will be like cost effective. It will not be cost effective. Whereas the ligands, if we have to choose like biomedical application, these has to be toxic free. Like it has to be get rid of DMF. It shouldn't contain a lot of sulfur molecules or nitrogen molecules. So these the toxicity of the ligands has to be taken into account when we use it for a biomedical application. The toxicity of metals has also been taken into account. But I think it is the balance of both in which it has to be accounted. So here is a question like, could you please explain about isoreticular synthesis again? So in this slide, we could see there are a lot of similar structures. We have seen a cube-like structure. So these cubes are a single unit of metal organic framework. But when we see this is the smallest cube, and it goes down and it becomes the largest cube. So this is the smallest cube, and this is the largest cube. So why it is larger? Because the cavity size is large, but the shape of the cube is always retained. So this cube is called as a larger form of this smaller cube. So such kind of a synthesis where the chemical properties, physical properties, and the structures are kept alike, but the core size is larger. So such kind of a synthesis is called as isoreticular synthesis. Did I explain enough? Thank you, Henry. Thank you, Akshya. Thank you, Priya.
So, any more questions, people?
Thank you. Can you explain the biocompatibility of MOFs? Biocompatibility of MOF. That's what Asa I said it for the previous questions. The biocompatibility we need to take into account for is the ligand is going to be toxic. What about the toxicity of metals? What about the size of the metal organic frameworks? So I think these all three has to be taken into account to check the biocompatibility. And though if we take all these based on literature, it cannot be biocompatible. And only when we test it, we can know, we can be 100% sure about its biocompatibility. Or to avoid or to make sure it is biocompatible, we can have a smaller MOF. We can take a less toxic or earth abundant metal, or and then those ligands which are not harmful to human bodies. Thank you all. Thank you, Ranjit. Thank you, everyone. Or Fe MOFs or magnetic in nature. Here I wanted to say not all ions are magnetic in nature, and there are very few magnetic MOFs are available, and the one I presented, Fe MOFs, is not magnetic in nature, which is not attracted by a magnet at a room temperature. These are not magnetic in nature because these are Fe2 plus ions, just Fe2 plus ions. Either it has to be like ion 0 compound or the combination of Fe2 plus and Fe3 plus to induce magnetic property in them. Thank you, Nitya. Thank you, everyone. Yes, Ashwati has a very interesting question. She has asked how come single metal and mixed metal MOFs have similar structure? We could see iron and nickel are two different metals, and how it can form a single compound. Based on this, we have to think on the ionic radius of these metals. So here you can see the one is Fe2 plus, sorry, nickel is in Fe2, nickel is in +2 state, and iron is in +3 state, which is the ionic radius of Fe3 plus and ionic radius of nickel 2 plus are close to each other. So this is why it is able to form a similar structure. So if you take I think only three metals are compatible like this. One is Fe3 plus, nickel 2 plus, and chromium 2 plus. The ionic radius of all these metal ions are similar in radius. So thus the structure is retained. I have to inform one more thing that if I have to prepare only with nickel, I will not get a similar structure. Only when we substitute only one nickel instead of one iron, we get it. If we substitute two nickel instead of two iron, the structure is not retained. I think I have answered Ashwati's question. Thank you.
People, we have left with few more minutes. So if you have any questions, you can just go on asking the questions now. You just directly go on asking the questions. There's no compulsion that you should just put it on chat. So you can just directly go on asking the questions.
Thank you.
Okay, Vasant, I guess people are done with the questions.
Yes.
Okay, so Vasant, what is the next kind of thing probably that you're going to take it on next Sunday? So what will be that?
Yes. If I have to, probably next Sunday will be fine. Like I can take it on next Sunday. I can just extend this and then give a little more light on it.
Okay, so people, the coming Sunday, that is on 12th, so you'll be having uh, the extension part of this particular entire thing. So today happens to be an introduction kind of thing. So the next Sunday you will be having the detailed one. So thank you so much for joining with us, people. Thank you so much, Vasant, for taking on this session. And people,
Thank you,
please,
Surya.
yes, thank you. Do check the chat here. So we have posted the feedback link as well as the review link of Easy. So please post your feedback on this particular webinar. The link will be active till 12 midnight, and you can just review as on Google page also, so that we'll be having the motivation to improve ourselves also. So thank you so much, everyone. Thank you so much, Vasant. So we'll wait for the next presentation session on Sunday, Vasant. Right?
Okay.
Sure.
And I thank everyone. I thank Suryawali for providing me the opportunity, and I thank all participants for the valuable time. Thank you so much.
Yes. Thank
Everybody,
you so
stay home, stay safe.
Yes. Thank you so much, Vasant, for that particular thing. Thank you so much, people. We'll meet you tomorrow evening, 5 o'clock, in another webinar of the same kind. So until then, bye. Good night.
Bye. Thank you to all.